Welcome to the last of our computational thinking series in IEP. I have to thank Erez and Kelvin for making this a great success. And I'm really happy with the turnout and the questions that we've had. We've had some great speakers, including Philip Mayman, who just appeared on the guest list, so thank you. It's a great pleasure to introduce my friend and colleague, George Varnavides. George is a graduate student at MIT in material science, and he's also being co-advised in physics at Harvard. He's worked on a lot of different languages, both theoretical stuff and computational stuff, since I've known him as an undergraduate. And he recently gave an IAP course where he demonstrated how to use Wolfram language, Python, and Julia together using Binder. And I thought it was really clever and a nice way to collaborate. And so I convinced him to give this presentation instead of me. And so I'm very happy to have George present to you today. So George, why don't you take the screen?
Sure, thanks, Craig. 1 second. Okay, can you see my screen?
Yeah, if you could zoom just a little bit, I think the audience will appreciate it. Okay, great. I'm going to go mute.
Okay, thanks, Craig. So like Craig said, myself and then two friends, Nina and Jovana Andrejevic, taught an IAP class on generative art, where we used sort of Binder, which is sort of to share fully executable environments of notebooks to do generative art using Python, Mathematica, and Julia. And Craig asked if I could sort of show some of that workflow, and we thought that would be nice. So what we're thinking of doing today is perhaps slightly ambitious, but three things. The first part is I'll just walk through what Binder is, how one would set about writing their own binder to include Python, the Wolfram language, and Julia kernels using a Docker file, and then two tricks on how you can speed up a binder launch and how you can separate the environment and content repos. And then I'll just really briefly show one example of the same system, a discrete dynamical system in both those three kernels, so Julia, Mathematica, and Python. And then at the end, we'll show these cross-language integration libraries. And in particular, we'll focus a little bit on Wolfram language external evaluate and how that can communicate with Python and Julia evaluators, and also Python's Wolfram client library. I won't be talking about PyCall and things like that in Julia, and I think I see people in the audience that are a lot more familiar with those than I am. So I guess that brings me nicely to my disclaimers. Firstly, I'll assume zero Docker experience, which is also where I was roughly a month ago when I started this. And I should say that, I'm fairly comfortable with the Wolfram language, but I'm increasingly less so comfortable with Python and Julia. So please be gentle with your assessment. And I'd like to thank Jesse Friedman and Arnaud at Wolfram Research for helping us get this set up with the Wolfram licensing. Also Binder Hub, they were flexible enough to allow some egress ports for us. And then finally, the example I'll show in the discrete dynamical systems is adapted from a lecturer at MIT's math department, Chris Rukowskis. Okay. So what is Binder? I've talked a little bit about Binder. Binder, at least according to the website, says allows you to create custom computing environments that can be shared and used by many remote users. And essentially, it's powered by this Binder Hub, which we'll talk about, which is a cloud service, and in particular, the one we'll use today is a free such Kubernetes server, which is mybinder.org. And essentially, what Binder does is that it takes a public repository, so we're going to give it a repo, a GitHub repo, or something like that stores all the Jupyter notebooks that you want to share. It might be you're teaching a class or a workshop. And then that's going to containerize. It's going to make an environment with the kernels you asked for it, and then it's going to share that environment sort of over the net, over the cloud, with students or whoever you want to share it with. And that environment will be interactive, so you can execute in it, and it will be fully reproducible. I mean, okay, there's some caveats to the reproducibility, but it will be fairly reproducible. So why don't I try and show that demo? Where did that go? There we go. Oh, okay. So this, for example, is one such binder ready repository. If
George, you may not be sharing the application. You think we're still seeing binder on the screen?
Oh, sorry, I had paused. Is that?
We see it now.
Okay. So this is one. Thanks, Craig. So this is one example repository that's on GitHub. So it's under binder examples, demo Julia. And it's what we call a binder ready repository. What that means is that it just has some configuration files here. In this case, it has a project toml and a manifest toml, which we'll talk about what they are in a little bit. But essentially what we could do is then we can navigate to mybinder.org, and then it asks us for the URL of the repository we want to use. So we're going to take this examples demo Julia. We're going to plug it in here. We are on the master branch. Fun fact, GitHub finally changed their archaic naming from master to main. And then you can click this launch button here. So if we click this, what Binder is going to do here, in this case, it's already been built. So we'll talk what this does, but it will read those configuration files and it will create a container, and then it's going to launch an instance. And this now is sort of this fully executable environment. And if I navigate to this demo here, I think this particular one is a Julia notebook demo. So it's going to try and start this kernel. It should be ready soon. And then, we can now interact with this notebook, and it sort of has this live Julia kernel. So, this interacts. If I wanted to change my kernel, this particular repo also has Python 3 involved, so we can, we can do things like this. Okay, so let me just go back to the presentation. I don't need that. Okay. So that's sort of binder, but like we showed, that particular example had a Julia kernel, and we could also change to a Python kernel. And in fact, this free service, like Binder Hub, they uses an open source tool which is called Repo to Docker. And Repo to Docker takes your repository, GitHub repository, and it builds these images on demand using Docker. And currently, the Repo to Docker has support, sort of built-in support for Python, R, and Julia. What it does is that if you have an environment YAML file in your repository or requirements text, if you're using pip, it will read that, and then it will install the packages that you asked for in the Python binary or environment that's in the repository. Similarly, for Julia, it will read project toml and manifest toml files, and it will create that environment. So if we want to use one of these supported languages, then Binder is very easy to work with. You just essentially make a repository that has these files, right? Just configuration files with the packages you want to install, and then the content you want to share. If we want to do slightly more complicated environments, and in our case, we want to include the Wolfram engine, what we need to do is that we need to specify our own Docker file. Also, I don't have access to the chat, but I trust Craig's going to stop me if there's questions in the chat that I should be addressing.
Will do, George.
Thank you. Okay, so we talked a little bit about Docker and Docker file. So what is Docker? Again, Docker is a tool, an open source tool, which allows developers, or which allows us to sort of deploy applications in what we call containers, in like a sandbox, which runs on a host operating system. And what it does is that, it allows one to really very nicely package all the dependencies that one would need to run whatever application one wants to run in a standardized unit of software. So, it's like virtual machines, but unlike virtual machines, containers don't have high overhead and sort of accessing the host resources. And yet, so they provide a more efficient usage of the resources of the host while still sort of providing this isolation of the application and the host resources. Okay, so that's Docker. And what Docker files are. Docker files are just recipes that Docker follows essentially to create an image. And if you're comfortable with reading Linux commands, Docker files are essentially identical. If you're not, we'll walk through them. Okay, so this is an example Docker file, a very simple Docker file. It has these keyword arguments in the and everything that's inside this run command essentially is going to run on the default shell in this case. And that's why I said anything in this run command is mostly identical to how one would write Linux commands. Okay, so let's have a look what's happening here. So the first line says from Ubuntu. And in particular, what it does is it says from Ubuntu : latest. So it's pulling an already pre-built Docker image as a base that it's going to start with. And in this case, this base is the Ubuntu or the Linux, a popular Linux operating system. And then the next couple of lines is that within this, base Ubuntu OS that doesn't have anything at this point other than, standard OS utilities, we want to install Python. So we're going to use, for example, apt-get, which is a package manager in Ubuntu, to first update our lists of repositories, and then we're going to install Python. And then our application here, we're just imagining a very simple case where we have two local files. We have one that's called hello.py and one that's called helloalternative.py. And we're just going to add both of those, right? So we're copying essentially files that we have on our host directory, and I'll show them in the next slide, to a location inside the container. So in this case, we're copying this hello.py file that we had in the current working directory to a directory inside the container called home, and then we're also naming it hello.py. Similarly, for hello.alternative, we're adding this. And then right before we finish we're going to specify an entry point. So, when we run our container, it's going to essentially spin off a Python process. And that Python entry point is going to execute this command, which in this case, the default command we're saying is going to be the hello.py. Okay. So again, just to make this example very simple and minimal, our two files that we're copying in just print two statements. The first one will print hello world. The hello alternative will print alternative hello. Okay, so then, what one would do on the command line to sort of build this image is essentially, you have to install the Docker client, but then you would run something like docker build Python image, which is sort of a name that we're going to give our built image, and we're telling it sort of build from the local directory. So it's going to find and it's going to read the Docker file that we had here, and it's going to build this Docker image. And then when we run it, after it's been built, we can say docker run, and we can run this Python image, this container that we made. And if we don't specify anything, then it's going to default to the command that we had, which was run hello.py, and then it just prints hello world, right? So this is a nice way of building a very simple Python application that is sort of mostly isolated from your host installation of Python. Of course, we can sort of access other things inside this container. So if we don't want to run hello.py, we can also supply it with additional commands that it would then run. In this case, if we say, actually, I want you to run hello alternative py, it's going to print alternative hello. Okay. So that was, I guess, very brief introduction to Docker and Docker files. Maybe I should pause briefly, Craig, if there's any questions.
No questions on the chat, but if somebody wants to unmute themselves and ask a question, that's fine too.
Okay. Well, I think I'll go ahead then.
I think you're ready to go.
Thanks. Okay, so that was that simple example, right? So let's go back to the Wolfram engine. So the first thing to note is, like, Binder, at least the public available resource, which is mybinder.org, works with public GitHub repositories, right? And after that's built, you can share it publicly with anyone, which is great, but it clearly poses challenges for licensed software, for example, the Wolfram engine. So recently the Wolfram engine released, the free Wolfram engine for developers, which is amazing. At the end of the day, it is, however, still a licensed piece of software. You can get a free license, but at the end of the day, it's licensed. So currently it comes with these two options. It can either, your license can either be node locked. So it's essentially tied to your machine. And that option won't work for us, mostly because we want to be building this on demand, right? In whatever cloud server mybinder.org is running. But as of 12.2, there's also this other licensing scheme called on-demand licensing, which is essentially, it allows one to reuse a license key called an entitlement ID. So you pass it this entitlement ID, and then for every kernel hour, you get charged some service credits, which for our purposes at least turns out to be peanuts. And thanks, Craig, for fronting that. Okay, so we're gonna look at how do we write a Docker file that's a little bit more complicated than what we just did to include, Python, Julia, and the Wolfram engine into a binder-ready environment. So this is the Docker file we're going to use. It's quite long, but hopefully well commented. I'm going to try and walk through it. So first, we're going to start again from an Ubuntu base OS.
George, quick interruption. The audience may be wondering if you're going to make this presentation available.
Yeah. So very soon, the entire repository, which is here, is already. So I can drop this in the chat. But soon enough, when we get to the binder stage where that is shareable, I will drop that in the chat. Okay. So here we're going to start from an Ubuntu OS. In this particular case, we're specifying we want Bionic, so 1804. And then, at the very top, we just specify some convenience or defaults, if you like, for the OS that are going to help us. We're going to say that we don't want the terminal to be asking us any sort of prompts, so we're going to make the front end non-interactive. Here, we're just setting up some locales. At the end of the day, I think this is all, it's important to do, but it's high level. I don't think these are any particularly exciting. Here, for example, I specify I would rather use bash instead of sh for the shell. And then perhaps before we go into the high level, the other useful thing that needs to happen in all sort of binder ready Dockers is that we need to specify a user so that we're not running our application as root, our super user. Okay, so and then again, these are just some very simple Ubuntu apt-get packages. So we want, at the end of the day, the distribution that we're going to give, and that's going to be shareable, it's going to have a terminal. So let's make it a little bit usable. Let's install things like less. Oops. Let's install things like, where did that go? Install things like less, git, curl, and here we're just going to bring some GCC compilers in it. And this next line is just some Wolfram engine package dependencies, which we're going to use later. Okay, so that was just set up, and then afterwards, what we need to do is that essentially we're going to split the Docker file in 3 steps. The first one is going to be, or I guess here we're defining some environment variables. So we're gonna make different directories, one for our Conda installation, one from our Wolfram installation. And then here we're passing this entitlement ID that I talked about before, right? And this, again, this other environment variable called Wolfram init or initialization, which again, its purpose is to pass this entitlement ID. Okay, but after we do this, the Docker file essentially has 3 components, and that's just installing the 3 kernels individually. But what I'm going to do, instead of just showing the Docker file, is I'm going to try and do this over here. Okay. So maybe I'll make the screen a little bit larger. So what we have here is I have a local copy of that repository. In this case, it's the binder environment, Python 3.8, Julia 1.6, and Wolfram Language 12.2. And what I'm going to do is I'm going to use the command line tool repo to Docker that binder uses to build this locally. So I'm going to do repo to Docker, binder environment, Python. So I give it the repository, which I guess, for clarity, the only thing that's inside this repository is essentially this Docker file that we're looking at the left. So if I run repo to Docker, it's going to sort of, okay, no such file. Oh, yeah, right. It's going to, so what's happening is that Docker is sort of stepping through one by one these commands, right? So it's going to step through Ubuntu 18.04. And in this case that I have here, it's using a local cache because I've already built this image before. And at the end, gives me a Jupyter environment inside this container that I can use. But perhaps this is slightly less useful. So what I'll do is I have here the output from the first time I build it to just walk through what this is doing. Okay, so again, from Ubuntu 18.04, and then it starts building these packages. And then, there we go. So these are just setting those locales, right? Setting that environment variable for the language locale. And then, okay, this is still all the sort of the initialization. So this is sort of typical apt-get output. I guess what I want to get at is here. Okay, so right now we finished with the OS installations, and what we have is this, we're going to install Jupyter. Essentially what we're going to install is a Anaconda-like Mamba installation. So what happens is we're saying I want to install Mamba version 0.74 using this installer. And it tries to find all the packages that you would need. So this is doing a regular Conda installation. So here we're installing using Conda. Okay. Scrolling down a little bit. So that was sort of setting up Jupyter, right? After that's done and Mamba finishes, which I think is right about here. Okay. Then we move on to the second part of that. So here, this was the Jupyter installation Mamba section. So we built Mamba, now we have a Jupyter kernel inside this environment. The next thing we want to do is that we want to set up a Julia kernel. So we switch back to being root user. We specify the Julia version we want to install. In this case, I'm running 1.6. And we're just downloading the Julia binary from the download page, and we're just untarring this inside the Julia path that we specified above in an environment variable. And what we do is that we copy the local project.toml and manifest.toml files that we had, and then finally we just compile this. So we start Julia and we ask it to pre-compile the packages that we're going to use. And here on the right, we sort of see that, you know, Julia-like output where it's installing the necessary packages that we're going to use. Okay, so that was the second part. Now we have a Jupyter kernel. Now we have And now we also have a Julia kernel. And the last thing we want to do, you want to add a Wolfram engine kernel. So that's sort of the third part of this Docker file. And again, we switch back to being root. And we're going to make some directories, Wolfram directory, and so forth. And similarly to Julia, what we're doing here is that we're downloading the Wolfram engine sort of installer from the net. And then we're just running that bash file, right? Install wolfram engine.sh. It's just a bash installer that will run this for us. And here on the right, what we see is that first it takes a while to download this. It's quite large. So let's just skip to the end where this was downloaded. I suppose. Okay. So we've downloaded it, and then we just run this installer. It's going to enter this Linux installer for the Wolfram engine. And after it's installing, it's going to tell you all the files that it installed. In this case, because we're running a verbose version. Okay. And then that's essentially it. So now we also have a Wolfram engine kernel installed. I think I'm almost done with this Docker file here. Okay, maybe I should be. Here we go. And then, okay, well, let's just go all the way to the bottom. So after we finished installing, the last thing that we need to do is that we need to manually sort of specify the Wolfram engine Jupyter connection. So there's this new there's a repository called Wolfram language for Jupyter, which we're going to use. So we simply sort of git clone that repository, configure, and then finally configure the Wolfram kernel to run with Jupyter. And after we're done, there's some entry point and default commands that we did before. But like we said before, the most important thing is that we just specify that we're user now and we're not root anymore, and then we can run. Okay. So that was the Docker file. Let's see what we have next. Okay. So and at this point, so first of all, the repository that I was using is here. Maybe I can post this in the chat. So this is binder environment repository. So that's in the chat. And, indeed, if we sort of take this URL like we did before and we go to mybinder.org and we just add this here, it will build it the same way that we saw before with the demo. Okay. There's two caveats with that. And so essentially what will happen if we were to do this is that when someone navigates to that URL with the binder link, if the image has not yet been built, repo to Docker will first build it like we just saw. So that would be the terminal output that we were seeing on the right. After it's built it's going to launch a binder instance. Whereas, and what like we saw before for the Julia demo, if the image has already been built before, it will simply just launch an instance. So this has, two problems, this approach. The first one is that, every time we make a new commit and we go to this new link, essentially Binder needs to rebuild this image. If our commit was just some comments at the end of the Docker file, won't be too much of a problem because it's going to use caching. But if it's, if it's at the beginning or if we're changing things like our dependencies or our packages, that might lead to a lot of sort of time to rebuild the image. And the other thing to note is that a lot of the time inside that build that we just did, well, first of all, it was getting the files, right? Like downloading that 1 GB Wolfram engine, takes some time. And there's also, there's time to build, like, Mamba has to find and solve the environment for Python, same as Julia has to pre-compile those packages and so forth. So, the next two tricks, if you like, are completely optional, but I found really speed up a binder build, and they make for a more user-friendly interaction if you're trying to teach like a class. So the trick we're going to use is that, remember, at the top of our Docker file, we had this from command, right? So that from command just pulls an already pre-built image, and that image could be like a binder image, right? So if we were to do this, then the only thing it needs to do is that it needs to pull those Docker layers, and it doesn't have to build, or it doesn't have to download the executables like we just did. Okay. So here, this is what we're going to use to do this is a GitHub action. So effectively, this is the YAML file for the action. Every time we push to that directory that I posted in the chat, so every time we commit and we push a change, what's going to happen is we're going to trigger this GitHub repo to Docker GitHub action. And what it will do is that it will build, it will do a repo to Docker local build sort of in the background asynchronously. And then after it's done, it's going to upload it to the free or to the public Docker hub. And then what Binder is going to do is then at the end of the day, just pull that already pre-built image. So this is nice, right? So like I said, we need three things. So I guess I'll just show this. So I think this is the repository. Okay, so this is the repository we were in. So if we go to actions, we have here our Docker Hub My Binder deployment. So we can have a look what this does. So this is the same YAML that I had in the presentation for the Docker action. And notice that it needs to know your Docker username and your Docker Hub password, right? But conveniently, we're not storing these in plain text. We're storing these as secrets in GitHub. So if I navigate to the Docker Hub, I have an account here. You can sign up and make one. And then if you go to your account settings, I'll probably stop, but if you were to click security, because we're recording, but if you were to click security, I think it shows you the security settings, and there you can specify that you want a password token. So once you have a free Docker Hub account, my username is Varnavides, and then my password is stored somewhere there. Then what we do is that we navigate to settings, and then here in secrets, and then here my repository already has these two secrets, so Docker password and Docker username. What you would want to do is that you want to go to new repository secret here at the top right, and the name of the secret will be Docker password and Docker username, and you sort of add your respective Docker username and Docker password. Okay, but back to the action. What happens now, if you look at the code here in the commits, so what ends up happening is that, oftentimes I'll commit something, right? And then right after that, like 15 minutes or 10 minutes later, however long it takes to build, the GitHub Actions bot then does its thing, and then it commits an update image tag. So let's have a look at what it does. There's this check mark here to indicate that the action succeeded. So if we click on this, okay, all checks have passed. If we go to details, it will tell us what it was trying to do, right? So here in checkout code, I believe, nope, I guess it's an update Jupyter dependencies. Validate information. Okay, yep. Oh, is that? Let's see, I think it's, oh, okay, here we go. So build and, this is okay, build and push. So what this was doing is that it was locally building, and it was doing exactly the same thing that I showed on the terminal. Step 1 out of 58, try to build this image, and then it's exactly the same. And again, in this case, the GitHub action is smart enough to use the cache from the Docker Hub as well. So this also goes quite fast. And once it's done, when this is done, It says here that it will post the checkout code. So what this does is that essentially it pushes the image that was built to the Docker Hub. So if I go to my Docker Hub account, I have gvarnavi, the same name as the repository, and there's all these tags, right? And these all got sort of automatically pushed by the action, and they have the git commit ID here, and in this case, we can also use latest and so forth. And then finally, after it's done building it, what the bot actually does is that it goes and it overwrites, or in this case, it makes a new file under binder Docker file, where it's saying, forget all the complicated instructions that you gave me in Docker file. What I'm going to tell binder is just this one line Docker file that says, from gvarnavi, this Docker Hub repository, just pull the latest sort of image. So now if we go, if we navigate to mybinder.org and we give this to it. Okay, well, it still found the built image, which is going to launch it. But had it not found it, that build step would have been that single line, right? Which is, I guess I can make a new commit to show it, but okay. So then that's that build file. And now, we've launched on Binder, and now all of a sudden I'm in this executable environment. But notice I currently don't have any notebooks here, right? I only have the environment YAML, which are just my Python dependencies that I want to use. And then I have my project and manifest TOML for Julia. Okay, so that was sort of tip number one, try and use the repo to Docker GitHub action. The second tip, or that I like to use, is sort of separating the content in the environment repositories. And the reason to do this is that every time you commit and you push that change, the repo to Docker GitHub action is going to try and rebuild this, right? But if you ever sort of design a workshop or done something like this, you often find yourself really making a lot of changes to the content, especially last minute, like this presentation, before giving like a talk or a conference. So you end up sort of committing last minute on these content changes, and you don't want to have to wait to build that and so forth. So we're going to use notebook git puller, which essentially will allow us to do the following. We're going to create the binder using the environment repository, which I just showed. And in fact, it's already open here. And what this gives us, well, first of all, if I go to new, we have all these 3 kernels that we asked for. So that's great. The other thing that we have is we have a terminal, right? So now if I have a different repository with notebooks, what I can do in this terminal is I can say git clone. And I can clone this repository here, right? And then if I go back to my home page, I now have this repository that has the notebooks that I wanted to look. And if I open one of those notebooks, now it's showing that presentation inside Binder, right? So that's, maybe I'll close this Binder now. Okay, so that's essentially the trick, right? It's let's have an environment, let's have a repository that just builds the Binder environment with all the kernels and the dependencies we want, and let's store our content elsewhere, and then we're just going to git clone it. Okay, and then finally, if you don't really want to see, have your students or the people that you're sharing this with have to do that, simple git clone step, there's this notebook git puller, which is misspelled here, notebook git puller that automates this thing. So they have this link generator. So you go here and you say my binder. Okay, what is my binder's URL? mybinder.org. We're going to use the public binder. And then the repository that you want to clone. So this is, or you want to have the environment. So this is the environment repository. Master. Okay, actually, I think it's main. and then the Git content repository that you want to clone. So let's clone that same one we were just at with the workflows here. Okay, and then if you actually wanted to then open a particular file, you can also specify it here. And we're just going to go with classic Jupyter. So what this does is that it gives you a link here. It gives you a URL. And that's the URL that you share with your students or with the people you want to share this with. Effectively, the first part of the URL just launches the environment, right? So it just launches the binder with main. And then it directs this to go to URL path and git pull, and then it just pulls the other repository. So here we have Varnavides, Python, Julia, and so forth. The automatic link generator is nice because you don't want to have to worry about escaping all these characters if you were to make this manually. Okay, and yeah, as you're waiting to clone, they have hilarious loading messages, which I thought was funny. Okay, and after all that, now we can finally launch our binder, right? And now we have this link. So first of all, I think the easiest way, I don't want to be, it's a long link, so maybe I shouldn't post it in the chat, but if you go to the environment repository that I shared in the chat, there's also this launch binder link. So if we click this, here it will tell us found built image launching, and now we're waiting to get an instance of the server running our environment. So this it depends. This sometimes takes a while. So don't be disheartened. And if it tells you that the launch failed, just refresh the browser. So
George, you want to take a question while that's launching?
yeah.
So there was a question in the chat window, and I'll read it for everyone. And it's from Philip Mayman. Here's the question. Is the right comparison to my binder a manual process where I create a Docker from a GitHub and then just run it on my own little cloud? Is my binder's additional value mainly in the convenience, or is there something technical it does that would be hard for me to do manually?
Right. So repo to Docker is mostly a convenience tool. So great question. So, and what I wanted to say with that is, essentially in most of the MyBinder, most of the use cases of MyBinder, right, would require configuration files, right? Most people that want to do this, they want to share notebooks that have, say, a Python kernel, maybe an R kernel and a Julia kernel. So in this case, it's a convenience thing because it just reads environment YAML files, it reads the manifest TOML, and it sort of makes the Docker file that we just showed. But no, like in fact, what we show doing is we wrote our own Docker file, and then essentially we just made a call to Docker, right? So to that end, I think it's mostly a convenience thing. That's true, but it is a very nice convenience, and it's very nice that they provide a public forum for you to do this. I should also say one can make their own binder hub, right? So if you have like if you have your own server somewhere, and maybe you also want to use private repositories, so you have things you want to share with collaborators, but you don't want this to be on a public Git repository, you can deploy your own binder hub that then builds these images on demand. Okay, so did that answer that question?
I think so. Philip can follow up if it didn't.
Okay. So that, and that was great waiting or use of the wait time. So now MyBinder launched, and it automatically sort of took us in, automatically Git cloned and then CD'd into this directory. And now we have our notebooks. So at this point, I was going to go to the second and third parts of the presentation, which was actually seeing some of these kernels, and then showing the cross integration. But maybe I'll wait a little bit if there's more questions on the binder workflow.
There was a request to paste the link again. Somebody got disconnected. I'll do that for you, George. Never mind. I think there's no more questions. You can go.
Okay. Okay. So that was the workflow of how one sort of sets up a binder that can then share his interactive notebooks with these 3 kernels. So now let's just very briefly investigate some of these kernels. So we're going to look at the same example very briefly. It's going to be a discrete dynamical system. And in this case, we're going to look at the de Jong map. And we're going to code this both with Julia, and then very briefly, I'll spend most time in Julia, and then I'll very briefly talk about the Python and Wolfram language implementations of the same code, and before we go integrating them. Okay, so what is a dynamical system? A dynamical system is essentially some set of rules that describe the evolution of a variable u in time, and that time can be discrete. And what we'll investigate in this particular example are these discrete maps, right? So these discrete maps, we can think as evolving using this equation of motion. So we have this state variable u at time n+1, and that gets evolved by an equation of motion or by a function, a higher order function in this case, that evaluates the current state at un, and then the number of iterations, and also any additional parameters or arguments that our function is going to take. And like I've already mentioned before, the bottom part of this notebook is adapted from Chris Rockhouse's excellent course that he teaches in the fall on this. Okay, so we're going to use, I guess I should have run this while I was waiting, but we're going to start. At first, we're going to use a library to do this. It's a performant library called Dynamical. Oh, well, that's interesting. That's exciting. Okay. Redefining attribute. All right, well, let's see if that causes a problem. I'm not sure what that is. So here we're just importing some of those packages, namely dynamical systems and some things to plot. We're also going to use benchmark tools to try and time this. Hopefully that doesn't lead to a problem. If it does, we'll take it from there. So we're going to look at the de Jong attractor. This is our equation of motion. So essentially, we have these equations that tell us that at point n+1, our coordinates x, y depend on the coordinates of the previous iteration according to this sinusoidal sort of coupled equation. So we write a function to perform this map. So it's a function that's going to, let's see if this, it's a function that's going to take our current state and our parameters. In this case, you know, we don't have a continuous time, so we don't have to pass it t, but for the sake of symmetry, dynamical systems sort of assumes that this is the argument form that you're going to pass it. So what it does is that it first unfolds this tuple of arguments that you gave it, then computes the next iteration, dx and dy, and then in this case returns the updated coordinate as a static vector, which is what we'll talk about. So we also need an initial state. So in this case, we're going to start our iteration by 1, 1. We're going to use some parameters, in this case, -2, -2, -1, and 2. So these are the A, B, C, and D in our equation of motion defined here above. So what we do here is that we define this discrete dynamical system using our de Jong, our equation of motion, our initial state, and our parameters P. And then using this sort of high-level library, we can get the trajectory for 100,000 points sort of quite easily, and it gives us back this two-dimensional data set of floats. If we wanted to plot this, we can plot this using, for example, scatter in Julia to look to see how the de Jong attractor looks like. So Binder is a great service, and it's obviously open source and it's free. The cost of that is that some of the cores are not the fastest. So if you download this and use repo.docker locally, or if you were to download the notebook, this will be a lot faster. But I think for sake of demonstration, this is fine. Okay, but speaking of performance, let's try and time this. So we're going to use benchmark tools. B time, which essentially, if you're more familiar with the Wolfram language, I believe is an equivalent for something like repeated timing. So now we're running this trajectory. So we're trying to iterate this discrete dynamical system called De Jong for about 10,000 iterations here. And it tells us that it takes roughly 500 microseconds each, and it only does 3 allocations. So this is quite good. It's quite fast, and it already doesn't make too many allocations. So that's good. But I think what I find to be the nice thing and the attractive thing about Julia, the appealing thing about Julia, is that, you know, we can write a minimal implementation ourselves, which is quite readable and easy to write, and it will be as performant, and in fact will end up being more performant in this specific example. So the way we're going to do this is that we're going to define what is known as a higher order function. So what this function is, it's a function that takes a function, and in this case takes an initial state, our arguments p, and the number of iterations n. And what it does is that it iteratively applies the map using the function that was supplied, and then returns the final result. The reason this is fast in Julia is, and I'm sure other people have better explanations for this, but it's because of type inference of the function, right? That functions have specific type, and therefore this higher order function is type stable, and it can, the just-in-time compiler compiles this down sort of efficiently. So let's write one of those equations of motion. So it's, again, our De Jong, and it's going to be this, what I call the naive version. It takes a state and the parameters, unfolds the tuple, just does the operation, then returns the list. And we can sort of start it by giving it an initial state with 1, 1 before, and using sort of our tuple or list for our parameters. And here we're going to do the same, right? We're timing this for 10,000 iterations. We're trying to compare this with sort of the library. So okay, it's not that much worse. It's about, you know, it does 800 microseconds, like this very simple implementation. But there's 2 problems, right? The first is that this implementation only returns the last point. So, you know, we don't get the full trajectory. So that's not as useful. And the other thing, performance-wise, is that it does a lot of expensive allocations. In this case, allocations on the heap. So, okay, let's tackle those problems one at a time. The first one is we want to have the full trajectory, but we want to do this on, say, statically sized arrays so that we don't make a lot of expensive allocations on the heap. So what we're going to do is that we have this solve discrete map save version where before we do our iteration, we just define a statically sized array because we know what the length at the end of the day of our iterations is going to be. We populate the first entry. Julia, like mathematics, like the Wolfram language, is 1 indexed. We specify our first entry by u0, and then we iterate our function and then populate I+1. And then at the end of the day, return the full list u. Oh, I guess I should have run this while I was talking. And then if we time this using b time, we'll see that we get the full trajectory. So that's nice. And then performance-wise, you know, it's 850 microseconds, which is obviously more than the 400 something that the built-in version was doing. But we get the full trajectory. So that's nice. And we get it as a vector of vectors in this case. So because, you know, we have this 2-dimensional data set, it might make more sense to have our statically sized output array be a matrix sort of beforehand, since we have a full 2-dimensional array. So here, instead of this vector of vectors, what we're predefining as our statically sized output array is a matrix. And the rest of the code is essentially identical, although note we have to sort of say which column of the matrix we want to be iterating over. And then when we time this, it's a lot slower, and it does twice as many allocations. It does roughly 20,000 allocations in this case, so it does 2 per iteration. So what went wrong? And the thing that went wrong is essentially this line here, right? In Julia, I think the default is to be making a copy every time you want to be slicing an array. So if instead we just use this macro at view to return a view of the object, not a copy, since we're not really, we're not changing that part of the array, then we can recover some of that performance and take the allocations back to where they were before.
Okay. Stephen Johnson just gave a useful hint that you can utilize later, George.
Okay, you
don't need to do it now, but it's good for, I think everybody saw it, just a different functionality of Julia.
Excellent, thank you. Just to make the comparison a little bit more fair with dynamical systems, we use static arrays before. So sort of arrays where we know what the length is going to be, and we're sort of predefining them to live on the stack. So we're going to do that here. So we're going to use using static arrays, which was the package we loaded in the beginning. And we're going to leverage this. So it's an identical code, but what we're changing is that we have our equation of motion sort of take as input and then return a static vector. And this, well, first of all, we're not making any allocations, and that is because now we're using static vectors, so that's excellent. And the second, so we're already sort of very close to the number of allocations, and in fact, I think less than the dynamical systems. And also, the performance is faster, right? I'm guessing it's because dynamical systems has to do some sort of, at the beginning, it has to have some logic to figure out what it's going to run, I believe. I'm not actually sure. Okay, just we can squeeze a little bit more performance out of this if we know that we're never going to go out of bounds, right? Every time you're indexing something, Julia is checking to see the thing you're trying to index is within bounds, right? So if it's a length 10 array, you're not asking for the 11th component. But if we know that our loop is guaranteed to do that, we can specify another macro, which is at inbounds, to do this. So we're going to do this for both our equation of motion and also sort of our higher order function that takes this. And this, I think, will be, again, a little bit faster. Okay, turned out to be, I guess, the same to that end. And then the last thing we can do to take away that last allocation that was left is we can actually pre-allocate and provide what that output array U is. So we just yank the allocation out, and we have, and then in this case, we can have 0 allocations. Or I guess we pre-allocated, but 0 allocations in the timing of this function. Okay, so all this was essentially to say how using very simple code, or like at least seemingly high level and easy to write and readable code, which was this line, so solve dynamic, and then our equation of motion here. So using these 8 lines, we can sort of outperform and do quite competitive thing. The other thing to note is that now the iteration loop is fast, and what we're returning is this list of all the points of the iteration. But as we saw before with scatter, that's going to be quite slow to plot. Instead, what we can do is that we can count the number of hits, right? We can we can paint an image by visitation density. So we can take that space that the iteration points can land on, and then we're going to discretize it into small bins, and then ask the question, how many times was bin I, j sort of visited? And then that's so what we're doing. So the first thing we want to do this is that we're going to write a mutating version of our attractor. So that's just an in-place version of our De Jong attractor. And then here, we're essentially mutating that array as we're going along. So we have a function that essentially takes du and it takes u, and then it just changes what du is in place instead of returning it, right? And then here, what we're saying is we're just going to iterate that function where we're in place changing du every time, And then before we go to the next iteration, we just switch the pointers between U and DU, and then we go faster. So this turns out to be quite fast as well. And since we're doing this, or I guess the motivation for doing this mutation as we're going along is that we can also, again, notice though, what this mutation means is that we're no longer saving the full array. We're only having that last or the current point, if you like, or I guess the current point and the point before. But this is fine with us because what we're going to do is that as we're iterating along, we're just going to be binning. So we're going to count. So we're going to be creating our bins. In this case, we're handing the bins beforehand, and then we're saying, okay, where did the first element of U land? Minus X over delta. What is the index of the bin? If that bin is within bounds, then increment that bin by 1. And then, yeah, this is just creating those bins beforehand and then sort of just solving that. And then the last part is just calling heap map, which is going to take a list of those or an array of those bins and color them. So I think I'm going to probably pause here for questions and perhaps the hint by Professor Johnson before we go on to the other two kernels.
Yeah, I don't see any questions, but I don't think you need to address the hint. It was just something I think for the audience.
Okay. Okay. So that was Julia, which again, it was just the discrete dynamical example. It was meant to show how you can start with a simple implementation and sort of write really quite performant code to do this. Very briefly, because it's the same example, I won't really comment too much about it, but we can do the same now in the same binder environment using Python. So we're going to import Numba that has this just-in-time compiler as well. So very similar functions to what we were using before. Here we're going to define our higher order function again, which takes that, in this case, it's out of place already. In place. And then if we time this for 10 to the 6, it turns out to be slightly slower than the Julia implementation. I think 2 times as slow, a little bit less maybe than twice as slow. Okay, and then we can write a binning logic. In this case, the binning is sort of post-process, just to see this as well. Oh, that's exciting. What happened here? Okay, yes. Name out is not defined. Really? Yeah. Okay, well, it looks like well, here we go. Huh.
Just so everyone knows, I did see this work. We've all had the experience of doing live coding.
Yeah, interesting. Somehow I thought, time it would allow for the variables to get defined, but I guess time it was messing that up. Okay. And then, so here we're just doing those counts. And then finally, I don't want to spend too long on this. This is just a little bit more matplotlib to visualize this, but it does the same thing. And we're going to get a very similar looking attractor in Python. Okay, the other thing to note is that binder, what we're doing now is post-processing binning. So binder gives you, in the free version, it gives you sort of so it gives you, a node that has 2 GB of memory. And in this case, our post-processing binning turned out to be too much. for that. So instead, let me just very quickly, just to see this. All right, our kernel died, so we're going to import NumPy again to find this. And let's do it for 2 orders of magnitude. Oops, no, we want that. Okay. And bum, bum, bum. So hopefully this works within the memory constraints. Okay, so same attractor, just slightly fewer points. Okay, and just perhaps to close the loop before we go to the integration, sorry to belabor this discrete dynamical points. In Mathematica, we can do the same. So this is now a Mathematica kernel in our binder. I'm defining a function called naive de Jong that takes the current state. It takes our arguments here and then returns it. We can call it once on that initial state, and we can very easily use sort of nest list to nest this 10,000 times and then just plot the results using graphics. Again, this graphics is going to be a little bit slow because it's trying to put all those points on a screen as a vector. And then in Mathematica, this post-processing binning is quite straightforward. We can use bin counts on this high level to get our bins. So, this nest list just returns essentially the same point as above. And then bin counts here is going to go from -2 to 2 in the X and -2 to 2 in Y in steps of 0.005. Count the number of bins, then assign it here. And then finally, we have bins plus 1 natural logarithm, passing it to array plot to get an image of our attractor. We can use the exact same logic as we did in Julia with compiling down to C and binning along the way. So this is using Mathematica's compile. I'm just going to note 2 things. First is this compilation target C, right? So, oftentimes, this allows you in Mathematica to compile down in C. Oftentimes, if you were writing this locally in Mathematica, you might have noticed that, oh, this sometimes complains you don't have a C compiler or that it can't find it. One of the benefits of, say, running applications or these kernels inside this containerized environment is that it's sort of guaranteed that these C compilers and in the Julia kernels that we're going to look at in a little bit are sort of at their default locations or wherever it is we decided to put them in our Docker file, and they can always be found. And then finally, this runtime option speed in Mathematica is essentially a quick way of doing the inbounds thing we did in Julia. So it checks it turns off bounds checking and also turns off overflow and underflow, I believe. And then finally, we have repeated timing, which is some analog for beat time that we saw before in Julia. And when we do this here, this is, so this is roughly about 60% slower. So this turns out to be faster than the Python implementation, but 60% slower than the Julia implementation. Okay, so that was that for the comparison of the 3 kernels. And the last thing we were going to talk about in this extremely long presentation is cross-language integration.
I'm just going to see if there's any questions, George. There's none in the chat. Okay. All right. Keep going.
Okay. I just shut down the previous notebooks while we were waiting. Okay. So now we're going to talk a little bit about this cross-language integration. And what I'll mostly be talking about is, running both Julia and Python from within the Wolfram language. And what we're going to, so we're going to use find external evaluator, or we're going to use external evaluate to evaluate these external evaluators, as the Wolfram language calls them. And essentially, as long as that evaluator, has a binary that can evaluate and has a zero communication, zero message communication, and a JSON package installed, which both our Python and our Julia environments do, then this works. Okay, so find external evaluator sort of just finds it. And like I said, I think this is one of the benefits of having a fully containerized environment where things are sort of stored in their default location. But if you're running this locally and you're not getting this target, specifically if it returns an empty data set, what happens is that, Julia, if you're downloaded a binary from the website, just installs everything it needs to install in that file that you extracted the binary in, and it doesn't sort of leak out to other folders. So oftentimes the Wolfram language might have a hard time finding it. If that's the case, and you're running this locally, navigate to a terminal, write which Julia, or using another way, find where it is that you stored that Julia binary, and then you can pass that into registered external evaluator Julia, and then whatever path that you had for your executable. And that should then return registered true or automatic and so forth. Okay, so the first thing is that we can use this external evaluator as sort of a single command, where essentially we're sending a command to the Julia kernel, and we're waiting for a result, and then we're returning that result and interpreting it in Wolfram language. In this case, we're passing a dictionary, or we're evaluating a dictionary in Julia, and it gets returned as an association in the Wolfram language. If you try running this and you got an error, and you're not running this locally, it might be that those packages, the zero message communication and JSON, aren't installed in your Julia environment. So you can just, again, navigate to a terminal, type Julia to get into the REPL, and then you can do either using PKG, or you can also go to the package type of package version of the REPL, I guess, and just add ZMQ and so forth. In my case, it should tell me, oh, interesting. I guess there was a change. Okay, so in my case, there's no change in my project TOML and manifest TOML, but if you're getting that error, there might be. Okay, so that was sort of a single shot, right? We're just sending a command to the Julia language and waiting for it to interpret the result and return it. The other thing that external evaluator allows us to do, which might be useful, is sort of to pass inline some template arguments. So if we had variables that we wanted to pass, or data, we can pass it using this template, a variable here. So this is sort of the same example as before, but it's sort of using a predefined global variable in the Wolfram kernel. I should also note that, obviously this is transferring and is sharing data and it's copying it. I don't think as of yet that would be great if there's works for that for external evaluate, to sort of spin off the Julia kernel and a Wolfram kernel at the same time and have them communicate and exchange memory. I believe this is what PyCal does, or PyCal does, which is much more advanced in this regard. This is just sending messages back and forth to some extent. The other thing we could do,
actually sending the data back and forth as text, is that right?
Yes, well, I think so. JSON to be actually precise, I believe.
Yeah, so pretty inefficient for large data.
Yes, correct. I should then the other thing that we could do, we can, again, as a single command, a single shot, if we have something that we want to say evaluate beforehand as a utility, instead of running using using PKG add and so forth, we can add a prologue to whatever session we're asking for. In this case, a Julia session, import that namespace, and then use it to execute whatever single command we want to do. The other thing we could do is that we can set up, an interactive usage. We can sort of start a persistent Julia session. So in this case, we're telling it start external session Julia, sort of the default Julia. We haven't really told it any of the packages yet. And here we can we can make another call to external evaluate, where in this case, the first argument of external evaluate is no longer Julia or whatever the package we wanted to evaluate is, but it's this persistent Julia session. So here we're just dividing a function that adds its two arguments. And then in a different invocation of external evaluate, again, in the same persistent Julia session, I'm calling add argument to 2. The other thing to note is I'm gonna take the suppression out of here, and we'll see what this returns. So the thing that it returns, because the only thing we defined, or the last thing I guess we defined in that session, was essentially a pure function, that gets returned as an external function in Mathematica, which I can assign to a variable. And then so Julia add arguments, and then I can use this using, I can call it using the same syntax that I would do in the Wolfram language. Again, this is a similar example where we're saying, oh, I want to use Julia's cubic root function. I'm going to assign it to a namespace here, and I want to call it from within Mathematica. But again, of course, it does that call. It sends the data and does the call in the Wolfram language. I'm not going to evaluate this line because it takes a while, but you can use it in other constructs, and this plot works as fine. It's not a list plot that I need to return a predefined set of points and then I just list them. This will do the call invocation every time it needs to query the cubic root function in the plot. And then to end sort of these persistent sessions, we can use delete object. Okay, and the last thing that I wanted to do, we wanted to show in Julia before we moved on to the Python client integration, is that here this returns sort of the basic bin in the repository that we had here. And in the Julia language, there's this concept of virtual environments, or of sort of projects and tomls, right? So we can, in this case, I know that I have a project, that if I go back in the home directory, we have this manifest toml and project toml that we defined when we made our Docker, our binder, that has all the dependencies that I wanted to use, for example, for dynamical systems. So what we can do here is that we can start an external session in Julia, and we can have it sort of go activate that particular environment and say use static arrays, and then we can implement that same discrete dynamical systems example we had before as an external function. The other thing to note, I'll just point this out. I'm using these, I'm essentially escaping with new line characters here. This is a little bit unfortunate, but this is just it's a consequence of using both external evaluate and the Jupyter interface, which just reads, or the way Mathematica exchanges with the Jupyter kernel. If you run this in the Wolfram language, like in a notebook, you don't need to do this. Start external session, Julia. These aren't necessary. Okay, I think in this case it might complain that I don't have static arrays. So let me not have a static vector. Let me just define this one for the sake of it. Won't return anything. So this works fine. It's just a matter of the. Since I opened the notebook, I might as well show it. The other thing you could do in the Wolfram notebook, you can start these external evaluate cells. So I just pressed what is it, the caret. So like this symbol. or left angle bracket, I guess. And it gives me this external evaluate cell. In this case, the default is Python, which we'll show in just a minute. But if you click on this, you can do Julia. And again, you can do the same. The first time you call, and in this case, this is a persistent session, which is nice. So I guess if I were to, this in the notebook, this code cell sort of implies a persistent, it implicitly calls start external session. Okay, so that was external evaluate and Julia. And the thing to note is that if we were to run this, which I won't, it turns out to be something like twice as slow, or maybe even more than if I just called the Julia session, like Professor Johnson said, mostly for the exchange, the inefficient exchange of data and so forth. In Python, this is a little bit remedied. So what I'm going to do here, I'm going to start an external evaluate session with Python. And I'm going to import NumPy. And then when I evaluate something like random rand, what it returns is this numeric array, right? So there's for standard data structures like NumPy data frames and so forth, Panda data frames, there is an efficient implementation or a more efficient implementation of sharing these and storing them, which is this numeric array, which we can of course convert to a normal expression using normal, but hopefully, if developers are listening, we can get an efficient implementation for Julia primitives as well, a more efficient implementation. Right, so this is just, again, that same example we did before. I'm going to start a Python session using NumPy and Numba, and then we can evaluate that same De Jong attractor that we did before. And in this case, it wasn't as slow as the Julia would have been, even though the Julia kernel in our implementation was in fact faster than the Python one because of this issue. I think I might have the same problem with the memory, but let's see if this happens to bin. Okay. So that's find external evaluate. The other thing that's interesting with Python is that the Wolfram researchers also made an open source project on a Python Wolfram client library that you can call Python, the Wolfram engine from within Python. This is, I guess it's a little bit convoluted, or in the sense that I start a Python session within the Mathematica kernel, and then within that Python session, I then create a new persistent Wolfram session. We can show this, and then we can just go to a Python kernel to have this be a little bit easier. So we're starting a new Python session, persistent Python session. And then in that session, we're importing these libraries, Wolfram client evaluation and Wolfram language WL, which is the Wolfram language expression syntax class defined in Python, and then just pure input Wolfram expression. We're going to start a persistent Wolfram session. And then here, we're calling this Python session, which calls the Wolfram session, which then evaluates the Wolfram expression integrate, sine x squared in this case. And we can access, we can define functions, and we can either use this global namescape, or we can also just define Python objects that are functions and then call them as we would. And then I guess as a tricky example, we're going to call that Python session, which calls the Wolfram session, and then to define an external function, we're going to assign that to a namespace in Mathematica, and then, or to a variable in function Mathematica, and we're going to call that using Wolfram language syntax. Yeah, I think this is all I had. This would be, unfortunately, I don't think as of yet this can have, a callback function, like the Python session can't really call back to the Wolfram session, to have it say recurse with the same function, like a Fibonacci sequence calling itself in the other language, which would be neat. But
So, George, I lost you for a minute. Can everybody hear me? Yeah.
yeah,
Okay, great. I hope George can come back. I think that was remarkably complete and quite a tour de force for an hour and a half presentation. As you all know, putting together an hour and a half presentation um, represents an enormous amount of time. George, we were just talking about how nice and complete and a deep appreciation for how much time it took to put together that very clear and useful presentation. I'm sure everybody would clap for you, but and I'm sure that everybody here would love to buy you a glass of your favorite beverage. I certainly will buy you more than just one glass of your favorite beverage when I see you again, and I look forward to seeing everyone. I think we have a
sorry,
little time
Craig,
for general questions. Go ahead, George.
I guess like, where exactly did I cut off? Because clearly I did, right? But like, did we go to the end of this?
I think you got a sentence from the end where you're talking about kind of complete implementation. A few of the developers from Wolfram said, yes, we're listening and we're on it. And so I think you said everything you wanted to say. You know, it's a short loss. Let's see, we've got some time, and I can imagine that George is pretty exhausted, and we can have a general conversation. You know, there's about 20 of us left, and so if anybody wants to speak up, I see that Colin has a question. Colin, let me know if you want to speak or you want me to read it for you.
Sure, I can just say it.
Okay.
So my question is about, you know, how does this sort of workflow transition to using it with larger like libraries that you're developing or packages that you're developing? So is there like a possibility to develop notebooks alongside like larger libraries?
Um, well, I don't know. I don't know if I should be the one addressing all the questions. I think this question, for example, Professor Johnson has a much better answer for, which is that I think, you know, Julia has a very sophisticated way of developing your own packages and distributing them. They're essentially like, you know, all of them have a GitHub page, and then that links to documentation. If you're referring to the binder, and the Wolfram language, of course, has its own way of developing packlets and so forth. If you're asking about binder and so forth, I will say I could see that being useful if one were to deploy their own binder hub, like a private binder hub, and then sort of share it with collaborators to do this. But you know, the public binder hub, I think the most utility that we found is as educators, right? Sharing fully interactive notebooks with either students or, you know, peers that you want to share a workflow with, or a, you know, a very simple sort of explanation of what you're trying to show. So I don't know how much you can push this for, you know, development code.
Yeah. There was an interesting question by Stephen Johnson about timeout problems potentially interrupting student workflows. I imagine you and several other people can weigh in on that particular problem.
Yeah, so Binder is has a 15. So first of all, like I said, if one were to do spin up their own, right, their own version of a binder hub, and then deploy that, then you're at the mercy of whatever way you have of scaling up and down your Kubernetes server that you locally set up in the local, and then you can set up whatever the resources are, right? Like currently, for example, the public MyBinder allows for up to 100 concurrent users. If you need more for a workshop, they're very nice. You can submit like a pull. You can open an issue and ask, say, I'm doing this workshop, I expect about 200 participants, and then they increase your quota. And then for timeout, currently after 15 minutes of an activity, it will time out. I haven't had issues where it just randomly dropped, at least the binder. Of course, the kernels can in Jupyter, as we're all aware. So I don't know. I think it's when that has happened with us, I've had students just refresh the page or relaunch the binder. And the nice thing about the binder hub implementation is that because it's a Kubernetes server that scales up and down, it takes a little bit longer for the first time you run it. When I'm developing and I'm on my own and I ask for these, I might end up waiting 10 minutes to get a binder instance. But once the class is already running and there's students inside the hub, that instance is a lot faster. So hopefully that deals with it.
I just checked. It looks like, so I had a session, I let it time out, and you can still save the notebook after it's timed out. So at least you don't.
Right.
At least you can download it to your machine after it's timed out. So that's losing everything necessarily.
I do want to.
It would be great.
Sorry.
I see your comment in the chat, Professor Johnson. It would be great for MIT to set up its own hub. So
I think that's something that Stephen and I may push on externally or internally at MIT. I do want to acknowledge Jesse Friedman, who's here, who has been the developer at Wolfram, who is making this whole containerized thing work at Wolfram. And so, Jesse, if you just want to say hello to all of us, it would be great.
Hello.
So thanks, Jesse. Any other questions out there? Well,
I'm sorry.
Go ahead.
Yeah, George. Do you have any like kind of real world use cases? Like today, you kind of demonstrated, where we're implementing the same thing in these two different languages, with different, some are faster than others. But are there cases that you can think of where like, just the best way, like it's not just an efficiency thing, but like, it's a practical issue of like you have to have this cross-platform thing. Just trying to get some ideas on like how this can be used beyond a sort of pedagogical setting or.
Sorry, just to understand, clarify, Hi-Ho, you were asking in comparing three different kernels, like the Jupyter Python or sorry, Julia Python or Mathematica, where a real world example where one would choose one or the other, or are you saying binder?
Where you would want to be using multiple, like where you're doing that integration that you're doing at the end. Because as we said, there is like this overhead, right, of like sending an external session, the shared memory, if we can get that working, but yeah.
I mean, like Arez said in the beginning, right? A lot of a lot of these languages have like a history of development, and there's already pre-developed packages. For example, if you try to do numerical analysis, NumPy is an excellent library, and then there's also a lot of symbolic sort of capabilities in Mathematica. So I would say, the best use case for this is when you're trying to leverage pre-built libraries in one or the other kernels. But you're more comfortable using most of your workflow in one language, and then you want to be making calls to do some specified API call or to do some specified numerical analysis in the other. That would be faster to do, for example.
I can throw a real use case in here. That's what we were talking about originally in the beginning of the session. I had this large analysis script for different forecasting models, and I wanted to use some that were not custom built for me, but kind of existed already in Python. So if I could have easily pulled the Python APIs and scanned many different Python APIs, but then brought all that data and all that forecasting into my automated script that already existed in Wolfram, it would have been, it's a big time saver.
I think that is, there's a parallel comment from Stephen just now about that, doing that as well. And so, yeah, I agree. Thanks, Erez. It looks like Max wants to say something. You may be
Yeah,
on.
I mean, I just had a similar like use case to add, which is just that you know, a lot of the Python packages themselves are written in C, so they're pretty fast. And so what I've found doing some programming in Julia, you know, when you're implementing numerical methods yourself, Julia is very fast. But obviously there are still fewer packages for Julia than for Python. But with PyCall, the overhead is quite low, I found. And then some of these fast like C packages for Python are pretty much just plug and play in Julia, which can be super useful.
Yeah, and so also Stephen makes this interesting point, that is the time at which different languages have had to develop. Wolfram language is now about 30 years old, and so it's got this huge infrastructure that works together. Other languages do other things better than other languages. I think what's really nice here is that being multilingual in languages gives you the ability to be much more flexible in the tasks that you want to do, and also switching tasks is my take on this.